Dear students, welcome to Orgo 1 Labs. This is your first lab of the semester. In this lab, you will use a technique called extraction to determine the partition coefficient of a compound. The compound used in this experiment is 9-fluorinone. So I'm going to kind of introduce you what is partition coefficient, why is it important, and then we'll talk a little bit more about how we determine it using the technique of extraction. So partition coefficient is determined to figure out the distribution of a compound in two solvents, and these two solvents need to be immiscible with each other. So in this particular experiment, you'll be using 9-fluorinone. This is your compound, and you're trying to see if I have two solvents. One could be water, one could be another organic solvent, methyl chloride. In this particular experiment, you're using diethyl ether. So if I try to mix this compound into these two solvents, which are immiscible, like oil and water, they do not mix with each other, how would this compound distribute in these two immiscible solvents? So for example, if I start with, let's say, 1 milligram of this compound, how it will distribute, how much will go in the water layer, how much will go in the ether layer, and what would determine that? To connect it to what you have learned in general chemistry, think about intermolecular forces. What kind of structures, functional groups are in here? What kind of a molecule and the polarities and dipole moments are in the solvents? Which parts of this molecule will make those interactions, those intermolecular interactions with water or ether? The more interactions this molecule can make with either of those, the more of this compound will be soluble in that particular solvent. So you could say if it's a polar compound, it will go preferentially in the more polar solvent. Okay, but generally the compounds may have structures inbuilt into them. For example, these rings are nonpolar. This has a dipole. So it has both polar and somewhat nonpolar components in here. So then you have to hypothesize preferentially it would go in which solvent more. Okay, so think about that. Think about, can it hydrogen bond with this one, or would have dipole interactions, or van der Waals interactions, or induced dipole interactions? What kind of intermolecular forces can 9-fluorinone make with water or ether? And then during the lab, you can, if you're not so sure, you can ask your TA and check your hypothesis before you start your experiment. Okay. So your goal is to figure out, if I start with a given amount of 9-fluorinone, how much or relatively what percentage do I expect it to go in the water layer and go in the ether layer? Okay. Now, coming back to the question, why do we care about this? Why do we need to know this? Well, let's say you're taking a medication. Our body has both hydrophobic and hydrophilic components to it. They're hydrophobic cell membranes, blood is mostly hydrophilic. So how any drug would distribute in our body will depend on its partition coefficient. Before the dosage of any medication is decided, we need to know how this is going to partition in our systems to figure out how much is actually needed to obtain the deserved effect. Okay, so that's one scenario where you need to know this. To know more about the technique, make sure you read the manual pages, the Mayo manual pages, which is the manual for this course. Make sure for this experiment you read these pages. There's additional information on the Canvas page. This video is on the Canvas page. Okay, so the key concepts are solubilities, how this compound dissolves in two different solvents, and those solubilities are determined by intermolecular forces. So review your intermolecular forces. And the technique used to determine that partition coefficient is extraction. So what is partition coefficient? As I said, it's a ratio in how a compound distributes between two different solvents which are immiscible with each other. Partition coefficient is written as Kp, and let's say the two solvents are solvent 1 and solvent 2, and X is the compound we are trying to figure out. For in this particular case, we are using 9-fluorinone. So X, you could say, is the concentration of 9-fluorinone in solvent 1, and here is the concentration of 9-fluorinone in solvent 2. So Kp is the ratio of the amount of this compound or solute in solvent 2 divided by solvent 1. So ratio has no units. Now, to simplify the things, every time we determine the partition coefficient, the solvent 2, which is on the up of this ratio, this is the organic layer, and the one in the denominator is in the aqueous layer. So you could change this equation to partition coefficient is the ratio of the 9-fluorinone in the organic layer divided by ratio amount in the aqueous layer. Now, amount is determined by concentration. You could use molarity, you could use any form of concentration, but to make it simple, we're just saying grams per ml, okay? How many grams or milligrams per ml in the organic layer and how many grams or milligrams per ml in the aqueous layer, okay? Now, further to simplify this, in this experiment, you would use 1 ml of both the organic layer and the aqueous layer. And since the volume here is 1 ml and here is 1 ml, they're both the same. And as long as the volumes are same, they cancel out. So partition coefficient at the end is mass of the substance, which is 9-fluorinone in the organic layer divided by mass in the aqueous layer. So if Kp is greater than 1, it means this compound has a higher solubility in the organic layer versus the aqueous layer. Organic layer in this particular experiment is the diethyl ether, aqueous is the water. Okay, so as I said, there are several applications of partition coefficient, drug distribution, also in anesthesia. When they give somebody an anesthesia, they need to know as the drug is inhaled, how much would actually is going to be effective. So they need to know the partition coefficient to see how much it would be effectively going into the blood versus the tissues. Okay, now how do we determine this partition coefficient? How do we use the technique extraction in the lab? Since both these solvents are liquid, we call it a liquid-liquid extraction. Extraction is also a purification or separation technique. This is a little bit advanced, but it's good for you to understand. Let's say you have a compound X and you're starting with 100 milligrams, and you know the partition coefficient is 2, which means if you extract it in 2 solvents, organic versus aqueous, it will always distribute in this ratio. So about 100 milligrams, and the partition coefficient, this is 2. So it's about 66 milligrams here and about 33 milligrams here. It means we got about 66 in the organic layer, which we can recover. The 33 is still in the aqueous layer. If we want to recover it again, we take this aqueous layer and then do a second extraction, okay? And then again, it will redistribute itself. So now we have about another 22 milligrams in the organic layer. So if we do 2 extractions, we could, out of 100 milligrams, very likely get about 88 milligrams into the organic layer. Okay, so it's a way of pulling or purifying or separating the organic compound. This technique is also used for that. Now, for this particular experiment, you would follow these steps. You'll take a 5 ml conical vial. You will weigh about 75 milligrams of 9-fluorinone and add 1 ml diethyl ether in there. Again, all the details are in your procedure. 75 milligrams of 9-fluorinone. Again, if you're weighing it, if you weigh 76, 78, or 70, it doesn't matter. Just write that number in your notebook. It's about 75. Just use that number for your calculations, whatever you actually weigh. You will take exactly 1 ml diethyl ether with the automated pipette and then add 1 ml water to the same conical vial. Since they are not miscible with each other, you'll see the 2 layers. The ether layer would be the top layer. Just like if you mix oil and water, oil is always the top. Ether has less density than the water, so it's the top layer. You're going to use a pipette, and your TA will show it to you how to use it. You're going to separate the 2 layers. With the pipette, remove this top layer and add it into a clean, dry test tube. The water stays into the conical vial. Now, as you transfer, again, you cannot be perfect, so there are human errors to that. So you're going to transfer some molecules of water layer into your ether layer. To get rid of that water, you're going to add some sodium sulfate, Sodium sulfate binds to water molecules, and the water in this test tube will bind to sodium sulfate, and that will kind of stick as a rock or a clumped up solid at the bottom of this test tube. Again, your TAs will explain it more to you. You're going to separate this liquid ether from that solidified or solid sodium sulfate by using a filter pipette into a new clean test tube. You should know the mass of this empty test tube. It should also have a boiling stone in there. And you're going to filter it so you're going to separate basically the liquid and the solid here. Okay, so the liquid will get connected here, solid will stay on your filter pipette, which serves as a funnel. You're going to evaporate the ether on a heating block. So ether will all evaporate. And what you have left here is the solid 9-fluorinone. You already know the mass of the empty tube. You weigh this again with 9-fluorinone, and you subtract the two masses, and you'll get the mass of the 9-fluorinone, which came into the organic layer, which is the ether layer. Okay, so let's say you started with 75 milligrams of 9-fluorinone, and as you did the evaporation, you obtained about 40 milligrams into your test tube. By just doing the math, you're going to believe that 35 milligrams is then in the aqueous layer, and you just determine the Kp. Kp is the ratio in the organic layer versus aqueous layer. Okay, these numbers are just for your reference. You're going to use the numbers which you obtained during your experiment. Your TA will explain all the actual handling steps of these extraction process as you come to the lab. And then you determine the partition coefficient. Okay, so that's the theory about the lab. Please reach out to your TAs if you have any additional questions. Thank you.